ኦኬ ሰላም ናችሁ? አይ ሆፕ ይሰማል ድምጼ። ኦኬ ታንክስ ሄኖክ። እንጀምር ወይስ ትንሽ እንጠብቅ? አይ ቲንክ አብዛኞቻችሁ ጆይን አድርጋችኋል። 18 ሰው ይታየኛል እዚህ ጋር። ሌላ ክላስ ነበራችሁ? እንጠብቅ ትንሽ።
Not actually. This is our morning class.
ኦኬ
Maybe we wait a bit.
ኦኬ Okay, seems like probably most of you has joined by now. So maybe you can get started. Okay, so for today, as you can see in that first slide there, we're going to talk about gravity separation. Now I know we talked about gravity separation last week, but last week we mainly focused on separators that use water as a media. And this week we're going to talk about those that use a dense media. So something denser than water typically can be used in gravity concentration. So today we'll probably focus more about how we can apply dense media separation in mineral processing or in ore beneficiation. So obviously some people may call it heavy media separation, some may call it sink and float. So depending on what is being used, you can have different terminologies, but in reality, all that we're doing is to use a heavy media for separation. So something sinks and something floats. So you can also say the light fraction of the ore is the float and the heavy portion of the ore is the sink. So you can also have a sink and float separation. So depending on who you see, maybe people may use different terminologies, but regardless, I think it should all mean the same thing. Okay, so what we're going to talk about, mainly we're going to talk about how we apply dense medium in ore beneficiation, and typically in this case, we'll talk about a couple of separators that are used in dense media, and also we briefly compare how dense media separators compare with that of other gravity methods where, for example, typically water is used as a media, as I said, maybe jigs, things like that. And the other thing we're going to do is how we assess the performance of a gravity separator or a gravity concentrator. So in this case, we use what we call washability curves. Now, if you remember from last semester, we talked about how we can assess the performance of classifiers using partition curves. And if you remember, for partition curve, we're basically using size analysis as a way of doing that. But in this topic today, mainly specific gravity is involved. So we can actually plot similar curves to that of size using specific gravity of particles. And we can also assess performance. So, but typically washability curves are used in dense media, and I will show you how we can construct washability curves and what information we get from washability curves as well. Okay, so what is a sink and float method, or how we use it? It's actually very simple. So when you think about it, if you, for example, use water as a media, and say you have particles with specific gravity of 1.5 and 2.6. Okay, so in this case, maybe one is a gangue and one is a valuable. If you put both these particles in water and you're not applying any hydrodynamics in the separator, most likely these two particles will sink simply because they're denser than water. So you would expect something with specific gravity of 1.5 to sink and something with specific gravity of 2.6 to sink in water as well, because we know specific gravity of water is around 1. How about we change the media density? So instead of using water, let's say we use a media or a fluid that has specific gravity of 1.9. Okay, so that's significantly larger than water in specific gravity. So in this case, you would expect the particle with specific gravity of 1.5 should float, okay? And the particle with specific gravity of 2.6 should sink. Again, mainly to do with the density of the media. In a 1.9 specific gravity media, particle with specific gravity of 1.5 is expected to float. So that's what we call the float as a product. If you were to have an ore where you have light and dense particles mixed together, you put this through a dense media, you would then expect the light to report to the float and the heavies to report to the sink. Okay, so that's why we say something like this can also conveniently called a sink and float separation. And the difference here is just the media density. From something that's about 1 in water, we go up to a heavier material that is with density of about 2.6. Kiros is saying he can't hear me. I don't know if everybody can't hear me as well. Can someone confirm if you can hear me? Kibru, you can hear me?
Yes.
Okay, very good.
Yes.
Okay,
Yes.
very good. Thank
Can
you.
hear you.
Okay, just give me a second. Okay, so as I said, the main difference is to use a denser media to help with separation. Okay. So what are these dense media that we're using in ore beneficiation? So back in the days, people used lots of this type of media for example, something that's made from particles, something made from ions. If, for example, you have calcium chloride dissolved in water, you would have a media or specific gravity with a media of around 1.35, simply because we know the calcium chloride ions will be denser than your water molecules typically, and therefore you should be able to produce a denser media. Okay, so instead of using something that's just water, pure water, with a media density of around 1, if you mix it with ions, or if you dissolve ions into it, you could probably make it denser. And I also did that exercise last week where I showed you separating in saline water is a lot more easier as compared to separating in just pure water. And we did calculate the concentration criteria to be able to see how gravity separation in a media that's denser than water is easier. But in any case, you can use something like that. You could use other hydrocarbons. A lot of them actually are now banned these days, obviously, to do with the toxicity and the fact that they are environmentally unfriendly. But back in the days, people used to use a number of organic-based solvents as well as heavy liquids or as dense liquids. And in this case, with this kind of liquids, you could probably produce a media that's significantly denser than water, and therefore they could be used, okay, as a media. And typically we mix these ones with some kind of alcohol to make the solution, and that media is used as a media for gravity separation. Other cases, for example, you could also consider using particles themselves or even bulky molecules and so on to produce significantly denser media. And that media is obviously used as a way of separating particles based on density. So probably to your surprise, most of these medias are not used in the industry currently, and there are reasons for it. So they said most of them are toxic, and also they're very expensive to buy. So they work well in the lab. So if you're working with something that's about 3 liters or 5 liters in a small scale lab, no problems. You can actually, check if dense media separation is a feasible way of processing your material. But when it comes to plant applications, where you're talking about very large volumes of media, it is probably going to be too expensive to implement for beneficiation. So most of the liquids I mentioned in the previous slide are not probably used in the larger scale industry. And therefore, people then started to come up with more environmentally friendly chemicals where you could suspend particles. Fine particles could be suspended in water, and that fine particle suspension can actually act as a media itself. Okay, so if I have very fine magnetite particles or very fine pyrite particles, which are suspended in water, as long as you produce a uniform suspension, you could actually use that as a media itself, and you can use it for separating coarse particles. So one example here is the use of, for example, magnetite suspended in water in coal processing or coal beneficiation. And there are a number of other examples where particles can be used as making a media. For example, back in the days, people use clay material or clay particles mixed in water to make up a media of about 2.3. So that's more than double that of water. Okay. Or you can use other particles like, for example, barite with particles less than 75 micron to make up significantly heavy medium. You can even use pyrite or other mineral particles which are suspended in water. And again, you're making a media with them, and that media can be used for separation. So these are just examples. For example, in coal separation, you can make a media of about 1.5. We know the coal is light, so that's the valuable part. And usually in coal ore, what we're trying to get rid of is a silicate material, because the silicate material doesn't burn, it doesn't have any energy value. So that's actually impurity in coal. So we can remove that impurity. Typically, it's denser than coal. So coal is maybe specific gravity around 1.1, but the impure material or the silicate material has specific gravity of more than 2.5, 2.6. So it's denser. So you have dense, impurity, and light coal. If then you use specific gravity of 1.5 for the media, then the coal floats and the impurity sinks. Then you can then separate the coal from the impurity by using a dense media. Okay, or for sulfide processing, maybe you can try to separate out the sulfides, which have specific gravity of 5, 6, 7, and so on, compared to the silicate gangue, which has specific gravity around 2.5. If your media has specific gravity of 2.8, then it's just between the waste and the valuable. So again, in this case, the waste, which is silicate, floats, and the valuable material, which is the sulfide, sinks. And therefore, again, you can make that sink and float separation to upgrade a sulfide mineral, or even something like a diamond, where you have diamond and kimberlite. Typically, the kimberlite is lighter, maybe specific gravity about 2.4, somewhere there. If you use a media of specific gravity around 2.7, then the kimberlite floats, while the diamond sinks, typically with specific gravity about 3.5 and above that. So again, you can separate kimberlite from diamond, which actually is one of the problems in diamond processing, because the kimberlite may also have some similar appearance to that of the diamond in some cases, and usually it occurs together with diamond anyway. So separating them from one another can be done through dense media and a number of other examples. So the whole point here, what I'm trying to say is, in typical sink and float separation, the media has specific gravity just between the light and the heavy. For most ores, the heavy is the valuable. For gold ores, for copper, zinc, lead, iron ore, for many of them, the sinking material is actually the valuable. The floating material is the waste. For coal, it's the opposite. Coal is light. So if you're mining for coal, the float or the floating material is the valuable coal, high-grade coal. What sinks is the waste. So again, in both cases, a sink float separation can be applied, and you can upgrade the material significantly. And also sink and float or dense media separation usually is done at a higher particle size or larger particle size as well, and that can be a benefit. So what do we need when we create a dense media to be used in separation? What are we looking for? For example, I told you that you could use particles suspended in water as a media. So when I say particles can be used, I, for example, mentioned pyrite or magnetite. So it's ground particles of magnetite or particle of pyrite are suspended in water, and we're using it for separation. So at least some of the requirements for this are that, for example, the particles should be very hard. If you put the particles to make up the media and they disintegrate and they break and they turn into very fine particles themselves, you're going to create very thick viscous pulp. Okay, so that's going to complicate your separation. So here, the particles we use to make up the media itself should be hard enough to withstand what goes on in the separator. They should be stable. For example, they shouldn't react with water and so on. And they should have reasonably high specific gravity. This is mainly to do with, for example, whatever particle we use to make up a media. If they're light particles and I want to make up a very high specific gravity of a media, then I would be required to add lots of these particles to increase the specific gravity of the media. And that would mean I would add lots of percent solids into the suspension, and that will make it very difficult for separation to happen. Most likely because the more particles you have, you would end up making a very viscous media to start with, and that will affect the separation. So what you want is come up with particles that are really dense. So you add only a tiny bit of that particle into water to increase the media of the separating solution very significantly. So again, particles we use to make up media should have sufficiently high specific gravity. They shouldn't settle quickly. Okay? If they're very dense and they settle quickly, again, they're going to be separated out. okay, and they're going to have the adverse effect. So again, we have to balance that between how much we add to make up the media and how large those particles are to make up the media, so that we get a nice suspension that's not really viscous. Okay, so some of the other considerations are you should also be able to generate those particles somehow. For example, if I'm using pyrite to make up the media, then I should have a way of regenerating the pyrite after using it for sink and float. Because, for example, you could use something like flotation, recover the pyrite and use to make up more media, and that media can be used for separation. So there are a number of considerations, but these are just some of the things that you should consider when deciding what type of particle you use for making up dense media. Okay, so what are the common ones? Galena, magnetite, ferrosilicon, pyrite, quartz. A number of these particles can be used for different applications. For example, if you use galena, we know galena is dense. You could make up um, a slightly denser density of up to 3 for specific gravity, because the specific gravity of galena itself is very high. So you add some amount of this into water, you're going to make the density of that media significantly higher compared to that of water. And also we know we can regenerate, for example, galena using flotation. If you use magnetite, you can then again make up a media with it, and you can generate it by using magnetic separation. Ferrosilicon is an alloy of iron and silicon. It's actually one of the most common commercially available material to make up dense media. Again, has significantly high specific gravity, and obviously you can use something like this to make up a media for dense media separation. Again, can be generated by magnetic separation and recycled. Pyrite and quartz, again, can also be recycled back using flotation. Pyrite floats really easily with flotation. Quartz, you can again float it easily with flotation. You can regenerate those by using flotation as well. So the whole point is here that whatever particles you use to make up a media, it should be dense enough. And if it's reasonably dense, then you can only add a small amount of that material to make up a reasonable density of the media, which can be used for separation. Okay, so what are some of the considerations? So in this case, for example, I say you could use mineral particles like galena and magnetite. For galena, you could probably generate specific gravity of a media of something around 3. And depending on how fine the particles are, you may run into problems as soon as you want to create a media of more than 4, because you would need to grind it finely to avoid the galena itself from settling, and that may again impart in issues with viscosity and slime and so on. So with galena, ideally you want to make a media of about 3 specific gravity. With magnetite, you can go up to 2.5. With ferrosilicon, it depends on the particle size you use. So as I said, ferrosilicon is commercially available for many applications of dense media separation. And depending on what density of media you have in mind, you can come up with different combinations of ferrosilicon. Even you can mix it with magnetite and so on to make up different medias. So typically, you again can target specific gravity of media of around 3, okay, using ferrosilicon of different combinations. Okay, so I already talked about viscosity as being one of the problems. Why do we care about viscosity? Because again, your success of separation eventually depends on how mobile the particles were. Okay, so you put particles in the media. If the media is very viscous, then particles can't settle quickly or they can't float quickly, okay? Which means you would have issues with efficiency of separation. So as much as possible, you want to maintain freedom for the particles to move inside your separating chamber. And in this case, you could have to worry about how viscous the whole media is, because in general, we know high viscosity will significantly reduce performance of a separator. Okay, so again, as much as possible, the volume of the solids we use to make up the media, and afterwards the volume we use for the media in terms of separation. So you have a separator, say separator is 100 meter cube. Okay, so of that 100 meter cube, the media obviously occupies a certain portion. And in this case, you may allow the media to occupy up to half of that volume, okay, to aid the separation between the light and the heavy. But how much volume the media itself occupies in the separator depends on a number of factors. For example, how wide is the feed in terms of size? Are you feeding a wide range, which includes fine particles, intermediate and coarse particles as a feed, or is it more restricted to only coarse particles that you are feeding? Or is it only fine particles that you're feeding? So depending on those, you could also have different variations in volume of the media itself in the separator, and that can be used to optimize the separation process as well. So of those particles that you could use to make up a media, I told you earlier that you could use any of these to make up a media for dense media separation. The denser the particles you use, for example, if you look at lead or galena or ferrosilicon, you actually need only a small amount of those particles to be added into, for example, water to make up the media. So I could use, for example, only a small fraction of ferrosilicon or galena or lead to make up a media of specific gravity of about 3. Okay. And at this stage, the viscosity is actually very low, which means these particles are suitable to make up a media of around 3. How about if you were planning to use quartz as particles to make up a media of specific gravity of 3? It won't happen simply because as you add more and more quartz, the viscosity simply shoots up. And in this case, it's simply impossible to produce a medium of specific gravity about 3 using quartz. Why? Because quartz to start with has specific gravity of 2.5, 2.6. There is no way we can make high density media using quartz. Magnetite, again, is a big struggle. So for example, with magnetite, maybe you can make up a media of about 2, specific gravity of 2, maybe 2.5. But as you go more and more denser, again, viscosity becomes a problem. So high viscosity is here observed when you try to make up a higher medium density using magnetite as well. So obviously this figure here simply shows you that we need to consider how the viscosity changes in terms of what particles we use to make up the media and in terms of the target specific gravity of media that we have in mind as well. Okay, so next I will talk about some of the common separators that we use for dense media separation. But before I do that, let's see if anyone has a question on what I've been saying so far. So do you understand the concept of dense media separation, or is there any question on whatever I was saying until now? All good?
Yes.
Okay. So if that's all good, then obviously there are different types of separators that we use in dense media, just like any other separators pretty much. But the construction of the separator itself is not actually very complicated. Okay, so compared to, say, other machineries like a flotation or something like probably using slightly more complicated hydrodynamics inside the separator itself. Gravity separators using dense media don't actually require complicated means. All you need to provide is a space for the particles to move with the media. And at the end of the day, all you need is a mechanism to remove the floating material and the sinking material. So you could actually use a big bus or a big cylinder or something like that to, cause separation based on specific gravity. You don't need any fancy equipment. But there are a couple of examples that I can mention in terms of the commonly used gravity separators employing dense media. So in this case, you could have static bus separators and centrifugal separators. So depending on what particle size you're looking at, you could use one or the other. Okay, and typically for coarse media for coarse particle processing, say when you're looking at particles that are 10 millimeter or 40 millimeter or 100 millimeter inside. So in millimeter size particles, typically we consider those as coarse particles, and we can use static bus separators for those. When particle size is smaller, then maybe just gravitational acceleration alone may not be suitable to separate particles into light and coarse, or light and heavy, and therefore we might need to employ some kind of mechanism inside the separator, maybe centrifugation, for example. And therefore, in those cases, you could use centrifugal separators for finer particle processing. So in static bus separators, obviously, the separator creates an opportunity to constantly remove the floats and constantly remove the sinks. And this could be, for example, done by simply scraping off whatever floats on the top of the separator as the floats product, and whatever sinks at the bottom can be mechanically removed as well. And that will give you the sinks yield, okay? And as I say, in cold processing, the float is valuable. And in this case, it could account for 80% or more of what is fed into that separator. For ore, the float is the gangue or the waste. And in this case, that may also account for up to 20, 30% of what is going into the feed of that separator as well. So again, your separator needs to allow for these proportions. So if I have lots of floats, then my separator should allow me to skim or to remove that float as quick as possible because the proportion of it is very high. Okay, so there should be that mechanism to allow for removal of the float as soon as possible. If a very tiny amount of float, then the volume of your separator should account for a large proportion of the sink. Okay, and therefore, sink is very large in quantity or in volume, so my mechanical arrangement to remove that continuously should be strong enough. Okay, so it should stand the proportion of large amount of sink that's going in the separator. So these are some of the considerations in terms of designing a typical dense media separation. So what does a static bus look like? So maybe it's a simple static bus separator is a drum. So what do we do in a drum separator? In a drum separator, you have particles fed from one end into the drum. So in this case, you could have light particles and heavy particles fed from one end, and with that we also feed the media. So obviously this is a continuously operating plant or a continuously operating separator. So as you feed the particles into the drum, this drum is allowed to constantly rotate. Okay, so it's not a static as such. So inside it, okay, is nothing happens inside it. But when you say static, we're not applying centrifugation or anything like that. It's just a rotation that's all applied to this bus or to this separator. So as particles come in, dense particles should sink to the bottom of this drum, and light particles should go to the top of this drum. So when you look at the inside of the drum, So this is what it looks like. So this is how it is rotated. Okay, it goes this way. And now as soon as particles are fed, the heavy particles will sink to the bottom of this drum. What happens then is, because it is constantly being rotated, these settled particles, or the sink, will be carried up to the top of the drum. And to be able to do that, we use lifters. And as you can see, these are the lifters that we use. Okay, so the lifters basically trap the dense particles, and they carry that dense particle all the way to the top. And as soon as it goes to the top of the drum, the particles should fall. Okay, and therefore they fall into what we call sink launder, or where the heavies are being collected. So the heavies are collected here. What happens to the lights or the floats? They always remain suspended in the drum. Okay, so they remain suspended in the drum. Sinks are coming and being collected here, and we're constantly pumping particles and medium through this chamber. So eventually what should happen is that these particles in the drum should be displaced. And as they're displaced, the light particles will exit the drum, okay, through this bottom chamber here. And as we said, sink, or the heavy ones, were carried here, and they went to the launder, or the sink's launder. And again, they will be exiting the drum through this mechanism here. So eventually you would have particles that are light and dense fed to the drum, sinks carried over to the sink launder and removed, while the floats that were not sinking, obviously, will be carried over and discharged as well. So you could have separation of particles happening based on light and dense. Who is calling? Someone is calling. Okay. Yeah, let's go now. Sorry guys, I was hearing someone calling, so I wasn't sure what's going on. Okay, anyway, so cylindrical rotating drum lifts particles to the top and discharge the sinks, and floats exit in a separate mechanism. And for example, you could make the drum to be really large in size. You could have up to 4.6 meter and about 7 meters long. And typically they run at about maybe 400, 450 tons per hour, but you could have large ones that run at 800 tons per hour as well, and can be used to process large particles. So in this case, usually in mineral processing, this is considered coarse particle, simply because, especially these days, we are processing particles that are below 1 millimeter. Okay, just because of the declining ore grade and so on, we need to grind to fine sizes to liberate particles. But when you have possibility to process coarse particles, say beyond 10 millimeters and above, you could use something like a dense media separator, simply because those are easier to manage, give you sufficient separation at reasonable performance, so they can be used for those purposes. Okay, so you could also have a slightly different arrangement for the drum separator. Instead of the one compartment where you have just the light or the floats and the sink and the heavy, okay, you could have two compartments. So in this case, again, feed containing all sort of particles with different sizes and densities is fed from one end, okay, together with two types of media. The first media is slightly higher in specific gravity. The second one is slightly lower in specific gravity. Again, similar mechanism, drum rotates in the first compartment. So I don't know if you see it, but this is the line here showing it two different compartments. So this is the first compartment, and this is the second compartment. I hope that's clear for everyone to see. So particles are being fed. In the first compartment here, as you can see, it's called low gravity compartment, or the media is low in specific gravity, which means the particles that float are only the lightest particles. So lightest particles float and removed by similar mechanism. Slightly denser and very dense particles will go to the sink and they're collected here with similar mechanism as what I showed you earlier. Now you have intermediate and heavy particles being sent into the second compartment. And in the second compartment, we have similar things happening, but now specific gravity of the media is slightly higher. So whatever floated in this first compartment, but with only intermediate density, will start to float. We call them middlings. And whatever sinks in this second compartment are only the densest particles. So if the particles are really dense, then they will still sink in this compartment and they will be removed just like the previous mechanism, while the intermediate particles, specific gravity that is, will be removed as middlings. So overall, you started with particles with various densities. Light ones are collected here as a float, middlings or intermediate densities collected differently, and then the heaviest ones collected differently. Again, you could have two separations happening in one drum, and you could produce three different streams, okay, for the heavy, for the intermediate, and for the light. Maybe you could go back and do either grinding on the middling to liberate them more and recycle them back, okay? Or you could just produce three different streams with three different options for whether you're sending it for further processing or you're selling it as a product. It will be dependent on what you're doing. Okay, so I said coarse particles reasonably okay to be processed using static bus separators. But in cases where that's not the case, okay, for example, in the static bus, particles were simply sinking under the influence of gravitational acceleration. When they're denser than the media, they sink. When they're lighter than the media, they float. As I told you, that's just the principle we're using. But in some cases, especially for fine particles, that may not be enough. Why? Because maybe fine particles may not have, although they are denser, if the media is of reasonable density and the particles are really fine, they may not actually have the ability to sink through that media. So they may not be separated out properly. So for those cases, we apply some sort of centrifugation using cyclones. And therefore, in cyclones, what we have is a situation where gravitational acceleration is replaced now by centrifugal acceleration. And therefore, instead of gravitational force, what plays a role will be centrifugal force, which is dependent on obviously mass of particle in the fluid and also the velocity here, tangential velocity. And therefore, if you use cyclones, you could operate them at reasonably higher capacity. You should be able to be working with finer particles and therefore maximize separation as well. So maybe something that took very long time to settle in a normal static bus may be removed very quickly or separated very quickly in the case of a cyclone or a centrifugal separator. And that's what they look like. So the way of operation is very similar to hydrocyclones. And if you remember, we talked about hydrocyclones last semester, how we can use them to separate particles into coarse and fine. Same principle, feed comes through here and it's introduced in a tangential motion, if you remember. And we said coarse particles were going here in hydrocyclone. Now in this case, heavy particles come here. And in hydrocyclones, small particles were exiting through the vortex finder. In dense media cyclones, light particles are separated out. So basically cyclones work based on the fact that heavy or coarse can be removed here, light or small particles can be removed here. Okay, so again, we can talk about either centrifugal force dragging the particles to the wall and exiting through here, or the drag force taking particles which are small to the center and dragging and taking them out here. So regardless of what happens inside the cyclone, you should have the opportunity to remove fine particles from, dense particles from light particles using a dense media cyclone. And if you look at them, they look something like this. This is an older picture from a lithium processing plant. Back in the days, they used to also process tantalite ore. And with tantalite ore, you can remove tantalite ore from as a silicate gang using dense media cyclone. But in any case, you have a feed coming from the top. And obviously with the cyclone and centrifugation happening inside the cyclone, dense particles exit through here and collected, and light particles pass through here and collected as well. Okay. Usually we use cyclones for fine particle separation, as I said, and you could have cyclone diameters of up to 0.5 meter in size. And maybe in comparison to what we do for hydrocyclones, we have them directly upside down, so from the top to bottom. I think the cyclones that I've shown you. But for dense media cyclone, we incline them to about 20 degrees. I think there's a lot of research around why you incline them or not. And most of the papers conclude actually inclining them doesn't actually make much of a difference. Okay, whether you incline them or you put them upright doesn't make much of a difference in terms of performance, simply because inside the cyclone you have significant pressure drop, and that pressure drop is not affected whether you put it upside down or vertically upwards or horizontally. The gravitational acceleration doesn't have much of an impact, therefore inclining them may not give you much of a benefit. But most commercial manufacturers will always make them inclined to about 20 degrees, and that's typically what you find for dense media cyclones. Okay. And if you look them operating in a plant, again, they look something like this one. And what you want to create, we want to create a media that's suitable for hydrocyclones, or in this case, dense media cyclones. It's possible that the media itself, if it's made from particles, you could probably even start separating the media itself into fine and large, or into dense and light. As I said, the dense media itself is made from particles that may undergo separation, and therefore you have a very poorly operating media to start with. But what we want is the media to remain suspended, okay, while the particles we're trying to process are separated based on density. Okay, I hope it makes whatever I'm saying makes sense to you. Because I said, if we make particles from magnetite, and the magnetite is used to make up a media, and then you're processing a lithium ore with this kind of media, what you don't want is the magnetite to actually separate itself in the separator. Okay, because the magnetite should remain suspended, and that should be helping you as a media rather than separating itself out from the media. Okay, so for that we typically use fine particles of magnetite, in this case, or ferrosilicon, typically sub 75 micron is used, and the particles that we're trying to process are way more than a millimeter in size. So there's a significant difference in size between the media particles and the actual particles we're trying to process. Okay, so that's one consideration. Media needs to be stable enough. And in terms of spheroid diameter, spheroid side, that is mainly affected by how much we want to process. So the capacity of your cyclone itself and so on. But obviously, if you make the spheroid size, for example, really large, what happens is fine particles, light particles will start to exit through it as well, and that will reduce the quality of the product that you produce. So in this case, you might reduce the grade of the concentrate, if you like, that you're producing. Again, if you make it very small, so in this case, if the spheroid is really small, it means you're not allowing enough product to exit. If you're not allowing enough product to exit, then you're also reducing the performance and the recovery. Okay, so that can be problematic as well. And the same is true with the vortex finder. So whatever exits here should be the light, okay? But if you make this really large, then you start allowing dense particles to exit through here as well. Okay, that needs to be optimized. And also you should vary the feed rate. So feed coming from here should be of reasonable flow rate, shouldn't vary considerably. If you vary it, you vary the hydrodynamics inside the cyclone. That again will ruin the consistency of the product that you're making as well. Okay, so comparison between, say, a dense media cyclone and jigs, which I talked about last week. For jigs, we use water typically as a media. So jigs are usually lower cost, are not requiring lots of operating reagents and so on. So they tend to be lower cost for processing and operation as well. And they can adjust really well. If your feed varies significantly, they can work really well. They can handle wide range of particle size. Okay, but they're not sharp. As we said last week, sharpness of jig separation is very poor, especially when you have loss of near gravity material. Okay, let's say your jig is separating particles based on density, and the density is 1.5. If you have too much particles near 1.5 specific gravity, then those particles can go either way, to the sink or to the float, or in this case, if it's a jigs, to the tailing or to the concentrate. So again, that is one of the issues we have with jigs, but with cyclones, that's a lot more better. So the control is a lot more better. So we can control separation gravity very well because the media helps a lot with that. And we can probably play with different specific gravity of the media as well. Okay, so we can vary medium specific gravity, and by that, we can cause different particles to separate at different points in the separation process. And that may help well. And typically they can also handle near gravity material as well. So again, there are cases where jigs are really useful, especially if you're not really worried about the quality of the product we're making, then jigs can work really well. But if you really want to maintain high grade product, then maybe you can consider something like a dense media separator. Okay, so in terms of performance, again, we can maybe compare different separators, and this is typically done for cold processing, but it can be applied for ore processing as well. So this is where dense media separators are. You could work at significantly high tonnage, okay? But in terms of tonnage, jigs are probably much more preferred. Shaking tables typically have low capacity, and typically they're also restricted to something like maybe beach sand deposit or high-grade gold ore and so on, which can be operated at lower capacity as well. And in terms of size range, you could have very coarse particles processed in dense media separation or in heavy media cyclones. Again, jigs can handle coarse particles, but the other ones are not really suited for coarse particles, especially when you're looking at particles that are 40, 50 millimeter in size. And in terms of efficiency, as you can see, heavy media cyclones are more efficient than any of the other gravity-based separators. Okay, and separating specific gravity very close to one another for jigs, but you can have slightly wider options when it comes to dense media cyclones. Okay, and you can talk about power requirements and so on. So obviously, at the end of the day, there's a number of factors that you would need to consider when you choose which one to go for. So is it the right particle size that I have? Am I looking at higher capacity operation or smaller capacity operation? Do I need to produce high grade concentrate or low grade concentrate, and so on? So there are a number of factors that you need to consider when you try to work with or choose whatever gravity separator for your operation. Okay, again, I will pause a little bit. And so in the next slides, I will talk about how you assess performance of a gravity separator, typically dense media separator. But before I do that, I will also see if there is any question. Elias, are you trying to say something? Okay, I'm not sure what you are saying, but yeah, I can't really hear what you're saying. If you have any question. Okay. So what are washability curves? Washability curves can actually be used to draw a number of conclusions about how well the plant is operating. Okay, so we know already, and I've probably mentioned this before, there is no such thing as 100% efficient operation, especially when it comes to mineral separation. There is always inefficiencies that could be just related to the particles that we're trying to process, because if particles are not liberated sufficiently, then you're not going to separate them properly. So there's no such thing as, for example, 100% liberation. If there's no 100% liberation, then most likely you're not going to also get 100% separation as well. But another factor here is we're trying to separate particles based on density, right? So for example, if you say density of 1.5, so what we're saying, if separating density is 1.5, we're saying particles that are lighter or with specific gravity of less than 1.5 should float. And we're saying particles that are denser or specific gravity of more than 1.5 should sink. But obviously in reality, you will have a particle that is very close in specific gravity to that of the separating specific gravity. So in this case, there could be particles that have specific gravity of 1.5, just like the media itself. So those particles can go to the sink or to the float at equal opportunities. Okay, or maybe you have particles that have specific gravity of 1.52. Although you would expect this particle to sink because it has very close specific gravity to the media, it probably will not sink that easily. So maybe it will float. Or maybe you have a particle that has specific gravity of 1.48. Again, yes, you'll expect this particle to float, but because it's very close to 1.5, it probably may sink. Okay, so those near gravity particles are very problematic, and we cannot achieve 100% efficient separation simply because of the issues associated with that. But we want to know what is the fraction of near gravity particles. So obviously, if we say 1.5 is the separating density, and we say 25% of my particles are very close in a specific gravity to this separating density, then I have a problem, because 25% of the particles may go to either the sink or to the float very randomly. Okay, so we want to know what proportion of the particles are near gravity or near the separating density. If they're only, say, 5%, all the other particles are either very light or very heavy, then we know again separation would be slightly easier, right? So again, we need to think about what are the proportional particles with density close to separation. So this curve here shows just an assessment of near gravity particles. So I say, for example, this is our specific gravity for separation. So the media maybe has specific gravity of, as I say, 1.5. So here, plus 0.1 specific gravity means particle with specific gravity of 1.6. Okay. And minus 0.1 on this scale shows particle with specific gravity of 1.4. So we have 1.4, 1.5, and 1.6. So if particle has specific gravity of 1.5, it has equal chance of going to either the sink or the float. So material will report to the incorrect proportion at 50%, which means it can go to either the sink or the float. But obviously, this curve can look very different. For example, you could have lots of particles, as I said, in this region, or lots of particles in this region, making separation very difficult. Okay, so in this curve here, for example, what you have is between 0.1 and 0. So let's say 0.055. So if this is 1.5, this is 1.55. So this should actually go to the sink according to my, expectation, because it's denser than 1.5. But if you have a particle that is at 1.55, this curve actually shows that it has about 19% chance of going into the wrong portion. Okay, so instead of going to the sink, it's actually possible that this particle may go, it has a very high chance of going into the float, which this case says 90% particles will go to the wrong portion. Okay, and you can do the same for any others. So obviously, the closer it is to the separating density, if particles are very close densities, as I was saying earlier, if it's say 1.51 or 1.52 density, then it will have very high chance of going into the wrong portion. So we want to know what is the fraction of particles with very close density to that of the separating density. And if we know that information, then we might need to think about carefully what separating density for the media we use. So instead of maybe using 1.5, we may say, okay, so there's lots of particles with media density of, with density of 1.5. So let's say maybe use a different media, maybe 1.4, and see what near gravity particles we get in that proportion and so on. Obviously, it also depends on what you want to reject and what you want to float as well. And therefore, you need to have that consideration in there. But regardless, we need to assess what is the fraction of near gravity material. Okay, so how do we do sink and float analysis? As I said earlier, we have the medium density just between the light and the heavy. Okay, so in this case, let's say the media has specific gravity of 1.3, and you have particles added to this media. All particles lighter than 1.3 will float. All particles with specific gravity of 1.3 or more will sink, if this was assuming 100% efficiency. Okay, then now you have this sink material. So you increase the density or the specific gravity of the liquid from 1.3 to 1.35. Now I make a slightly denser media, if you like. Then I say now I had particles sinking in here. If I increase the media density, then some of the particles may float because they have density of less than 3.5. Okay. And if particles have density higher than 1.35, then they will sink again. So whatever I collect here are floating in this specific gravity, but they're sinking in this specific gravity, must be because they have maybe specific gravity between 1.3 and 1.35. Let's say particle with specific gravity of 1.34 or 1.32. So those ones will be collected here. Now again, particles are sinking here in 1.35. I increase media density to 1.4. Again, whatever sunk here in 1.35 may now float here in 1.4. If particles sink, it must be because they're denser than 1.4. If they float, it must be because they're lighter than 1.4. But they were sinking here, must be because they are, heavier than 1.35. So again, particles with density between 1.35 and 1.4 will float here. And this process continues. So again, I can have particle with media of I have media of 1.45, continue the process. I prepare media with 1.6 and so on, and process continues until I'm happy with what I'm doing. So when you think about it, this is actually very similar to what we did for particle size distribution, where you had a sieve, okay, and on top of that sieve, maybe you had a coarse sieve size. Particles passing through that sieve are collected in the next one. If they pass through that, they will be collected in the next one. If they pass through that, they will be collected in the next one, and so on. And at the end of the day, you can determine particle size range depending on the sieves you used. So this is very similar to what happens in a sieving process. So at the end of the day, after conducting, say, sink and float for 5 media with 5 different specific gravities, you could have 7 products or 6 products that you can consider as sink and float, and you can assess what you have in that sink and float. Okay, so then at the end of the day, you can make some decisions in terms of what is the ideal specific gravity of a media to be used to obtain this much recovery or this much grade. Okay, so the more you do this, you can decide where to stop based on your target recovery and based on the quality of product you would also require at the end of the day. So separation can be just quantified based on recovery or yield or expected recovery, which is theoretical. If I say 1.5 is my separating density, anything above that should be recovered. So that will give me my theoretical yield, okay? Or the difference between the actual and the theoretical, which will give you the yield error, and you can just use that to, again, assess separation performance. Or we can construct different curves, the washability curves, and so on. And just like we did for size, we can actually do the same thing for gravity separation as well. Or we can calculate imperfection, errors, and so on, again, based on the performance of the sink and float test. So I'll talk about how we can achieve those in the next slides. Okay, now when you see this table here, I'm sure it looks overwhelming and it's very large table. And maybe could look very confusing already to start with, but what I'm going to show you subsequently is how you can get different information, construct this table, and once you construct the table, you can then come up with different curves to assess performance of gravity separator. And washability curves are actually based on this table here, where we look at different scenarios, including, for example, cumulative loads, cumulative sink. If it's a coal, then you could also look at ash content, and you could work at separating density and the differences between different separating densities and so on. So I will talk about how we do this one, okay, and what they mean. So from a sink and float analysis that you can conduct, that you have conducted, you could have floats ash curve, for example, for coal, cumulative sinks ash curve, again for coal, instantaneous ash curve, specific gravity or relative density curve, and distribution curve. These all tell you different things. Okay, for example, a high proportion of plus or minus 1 specific gravity distribution curve may tell you that whether separation is easy or difficult, or a low percent may tell you whether separation is easy or difficult. So I will, again, don't stress too much about the things I'm passing now, because I know I'm going to come back to them eventually anyway. So then at the end of the day, what you'll find is washability curves that look like this one. So where you can plot cumulative floats curve, instantaneous ash curve, cumulative sink curve, distribution curve, and relative density curves. What do you find from this? For example, you want to say, if I'm targeting a product that has, say, maximum of 14% ash, what is the recovery that I get at this ash amount. So if you did your proper washability curve, then from the cumulative floats curve, you can actually tell that to get a product of 14% ash, the recovery you should expect is about 68%, which means you're going to lose about 32% of the coal because you're targeting a high quality coal as a product. Okay, then you can talk about, then if I'm targeting 14% ash, what is the separating specific gravity that gives me this? Okay, this product. And it says here from the relative density curve that to be able to get 14% ash in the product at 68% recovery, you could actually use a media that has specific gravity of 1.5. Okay, so that's the media that I'm going to make to prepare that. And again, if you then say what is, so that is the total ash percent expected, but what is the maximum that any particle can have? Okay, in that 14% ash, the maximum, some particles in this case can have a maximum of 24% ash in them, but the average is 14%. Okay, that is read from instantaneous ash curve. And from the distribution curve, what you get is difficulty of separating. For example, if you were to use 1.5, the distribution curve tells you that the corresponding cumulative float is 44%. And if you go back to this table here, at 44%, you're looking at separation becoming really, really difficult. Okay, so you're going to have hard time applying sink and float experiment to obtain that quality ash. Okay. And you can also look at cumulative sink curve. So of the west, you can look at the whatever floated, which is most likely silicate material. Then you say, I recovered 68%, 32% went to the sink. In that 32%, you have 55% ash. Okay, so that's what we read from a cumulative sinks curve. Okay, so as I say, don't stress. I know I rushed through that. Okay, maybe you have no idea what happened, but at least from what I said, you can see that there is some relevance in doing these washability curves. And from those washability curves, you can actually make some very good conclusions to optimize your operation. Okay, I'll come back to that. Okay, and I'll probably do it very slowly so that everyone follows what we're trying to do. Okay, so how do you quantify efficiency? As I said earlier, you can probably, just like we did for quantifying performance of hydrocyclone or efficiency of hydrocyclone using partition coefficients, we can do exactly the same for dense media separation. The difference is instead of particle size, we're using specific gravity. Okay, so in hydrocyclone or in classification, particles were separated based on their size. In gravity separation or in sink and float, particles are separated based on their density. So we said in hydrocyclones, for any given particle size, we can see where that particle reports to. So for example, does it report to the underflow in comparison to the feed? And based on the quantity reporting to the underflow comparison to the feed, we said we can work and construct partition curves, if you remember, and we do exactly the same. In this case, instead of size, we just use specific gravity. Okay, specific gravity reporting to that particular range, okay, compared to that material present in the feed itself for that particular specific gravity range. And based on that, we can talk about separation efficiency. So in this case, when I say specific gravity range, so if I used media with various densities, okay, so in this case, the first media has specific gravity of 1.3, next one has 1.35, next media has 1.4, 1.45, and so on. So what we're doing is we take the material, put it in a media of 1.30, whatever floats is recorded here. Whatever sinks goes to the next media, Again, in the next media, whatever floats is captured here, whatever sinks goes to the next media. Again, whatever floats here goes here, whatever sinks goes to the next media, and that's how we construct this using that diagram I showed you earlier. So then what you can do is we take samples, okay, floats from the first operation at 1.30 specific gravity. I take that float, I can do ash analysis on it. So basically you can submit the sample and they will tell, basically they burn the sample because it's coal in this case, and whatever remains would be the residue, and that is what tells you the ash content of the coal. Okay, that's the material with no energy, mainly made from silicate. You can actually quantify the ash content of the sample that's being given to you. So in this case, so these numbers here show the fraction of particles that report as floats to this specific gravity range compared to the total that we have captured in the floats. And this number here simply tells you, you took a sample from here, analyzed it for ash. Took a sample, analyzed for ash, took sample, analyzed for ash. Okay. And then based on that, you can actually work out how much particles or how much material is collected in the float and how much material is rejected into the sink, and what is the amount of ash in each of those products as well. Okay, so once you do that, you can then construct what we call the washability curve, not the washability curve, the efficiency of a gravity separator. And based on those, you can then study or analyze whether the gravity separator is giving you a reasonable performance or not. So whatever we have here is analogous to overflow and underflow for a hydrocyclone, if that makes sense. So here in hydrocyclone, we have size ranges. Okay, so coarse size range, and we are going slowly decreasing the size. Okay, but in specific gravity or in gravity separation, we're going from small media density to higher media density. And for that, we collect all the samples for each of those ranges, and we express that as a percentage. Okay, and if I want, I can quantify how much ash is here. And then I also collect, so whatever doesn't float must be because it went to the sink. And in that sink, again, you can see what fraction of material is reporting in this density range, in this density range, in this density range, and so on. And therefore, obviously, the sum of all these should give me 100, and the sum of all these should give me 100. So let's say particles fed into separator goes to either float or sink. Okay, so you can talk about split. So again, if you remember for hydrocyclone, we say underflow split 80% or something like that. Okay, we can have split again, similar here, where we have maybe 70% goes to the sink, 40% goes to, 30% goes to the float. So that will be your split. So your MFT is mass of the float or the split to the float, and mass of the sink here simply represents split to the sink. Okay, so if we then add this one with this one, you get the feed, and then the partition curve simply can be obtained by, for example, dividing the floats with the feed or the sinks with the feed. So again, if you remember for hydrocyclone, we're doing underflow to the feed, and we were constructing partition curve based on that as well. Okay, so again, you can look at each of these. So how we construct each of those columns, I think you can probably read through this one. Okay, so in this case, this one is we collect whatever material in all floats, and we express percentage of each of the floats for each of those specific gravity range. And for column 3, we quantify all the things and whatever fraction in each of those for all the things is quantified. And for column 4, we just take the split. So if this is my material, and 80% splits can be obtained by working out that. And if this is 80, then this has to be 20, then that can be determined. And therefore, multiplying this column by 80 will give me this. Multiplying this column by 20 will give me this, as long as I know the split. Okay, so read through this one slowly, but very similar to what we did for the hydrocyclone operation. So at the end of the day, you would have partition curves, just like we did for the hydrocyclone operation. Okay, so that will give you, so column 4 by 6 or column 5 by 6 will give you something like this one. Okay, so partition curve versus, now instead of the size, which we did for hydrocyclone, we have specific gravity. And here for hydrocyclone, we, for example, had mass splitting from feed to the underflow. In this case, for specific gravity, we could have material that went to the floats compared to the feed, or material that went to the sink compared to the feed. Okay, so that's what we have here. Okay, so then you have partition curve, and say, for example, at 1.50, partition curve is 50. So if particle has a density of 1.50, then it has equal chance of going to either the sink or the float. Just like a particle size, we say separating size for hydrocyclone. At that D50 value, particles have equal chance to go to either the fine or the coarse, or overflow or underflow. The same here. So denser particles above this should report, what's this one? So denser particles should report to the denser portion. So if my separating specific gravity is 1.40, it looks like this one is taken for the floats. So floats versus feed is what probably gives you this one. But regardless, or you can do the other way around, the sinks versus the feed, then you would have slightly different values here. So maybe instead of looking like an S, you would have something looking like a Z. Okay. But regardless, we can then predict what particles should have gone to the float compared to what I initially had in the float. So if particles are lighter than 1.5, I'd expect all of them to go to the float. Okay. So in this case, this is what it's showing. So if all of 1.4 particles went to the float, this should be 100%. But as you can see here, it's about 90%. It's telling me that about 10% of particles that are 1.4 in a specific gravity, rather than going to the float, they actually went to the sink. So that's what this number here tells me. Okay, and the same is true here. Okay, for example, if you had particle with specific gravity of 1.6, this curve is telling me maybe about 15% of them, instead of going to the sink, actually they went to the floats. Okay, so that's why this curve again can be very useful in assessing the performance of a gravity separator. Also, from that curve, you can calculate probable error and imperfection. From that, you can make some nice conclusions as well. Okay, so ideally for a probable error, you want it to be close to 0. Again, imperfection can be calculated using this formula as well. And this is just comparison of some of the different gravity separators that we have and their expected errors. So as you can see, closer to 1 for heavy media cyclone is expected to be highly efficient. Heavy media bus expected to be highly efficient because of the fact that they have a lower probable error. What else you can do? You can actually put some bits, some specific bits with known density into your heavy media separator as well. And based on where these bits go, so they have different densities. And if you know you added 100 bits into the separating chamber, and you know exactly the density of each of those 100 bits, you would expect them to go to either the float or the sink based on the density. And you can actually use that as a guide to see how good your separation is as well. Okay, so some of the things that you can do to assess the performance of a gravity separator may involve just do some basic tests, including a plastic bead. And also you can use some of the information from here into your process design as well. So for example, you're looking at the new deposit, you have done your sink and float test, you have constructed your separation density curve or partition curve. Then based on that, you can make some nice conclusions. So if I say, if I target this much percent or that much percent, what is the expected recovery and grade and so on. And those can be predicted and that can be inputted into your design as well. And there's some of just applications that you can consider from a typical sink and float analysis. Okay, so what I thought was to go back and do a couple of exercises on how we construct the partition curve, sorry, the washability curves. And from those washability curves, I will show you how you can determine certain scenarios, okay, to inform how you can run a typical dense media separator. But before I do that, I think it's better to maybe pause a little bit and see if anyone has a question. Any questions? No question. Okay, so it looks like my slides are not modified. Okay, so let's go back and see if everyone can follow me when we do this exercise and complete that table. So the table I'm talking about is this one, from which we can draw different curves. And from the curves, we can make some nice conclusions about the performance and the expected recoveries and grades of the sink and float experiment. So if you conduct a sink and float analysis using a range of media, so in this case, a media with specific gravity of 1.3, 1.35, 1.4, 1.45, and so on. So what this table shows is the material that is being collected at each stage. Okay, so this one here, I think I will use my, so this material here, this number here shows float that has been collected for each of those gravity separator or for each of those medium that we used in the gravity separator. So based on this data you have here, you are asked to draw these curves. And obviously, once you draw those curves, you can use them for different conclusions. So I'm not sure if everyone understands what this shows to start with, but what it shows is you do a sink and float at 1.35, sorry, at 1.30, and 9.5 is of all the float you collected, 9.5% is in this range. Okay, and when you come here at 1.35, of all the floats you collected, 9.7% is in this range. And this here shows at 1.4 specific gravity, you conducted the experiment with a media of 1.4, and of all flows you collected, 13.4 is found in this range. So you can then take whatever material floated here and do quantity of hash. And in this case, for this range, the quantity of ash is 5%. And at 1.35, you collected this material and you quantified the ash to be 8.1, and so on. So all this shows that the amount of ash in each of those fractions of floats that you collected for each of these specific gravity of the media. Okay, so I don't want to go any further. If you don't understand what this shows, I think it's better to first maybe repeat myself if I have to, so that everybody understands what we're doing here. Okay, otherwise there's no point in trying to do anything further on a data that you don't understand how we even got it to start with. Okay, so I need some feedback from you guys. Does it make sense? It's really confusing, or you know, if you have no idea what I'm talking about, that's fine. Just let me know and I can explain slowly what's going on. Okay, so what I mean is just to make sure everyone understands how we're getting these values. So I have a feed coming. Okay, I have a feed coming, put it in a media of 1.3, specific gravity, light particles float. I take this, put them somewhere, dry them. Okay, so that's my float in 1.3. I take the sink, put them in a media of 1.35 Sg. Whatever floats here, I collect it and dry it and analyze for ash content. Whatever sinks here, I take them and put them in a higher media, 1.4. Whatever sinks must be because they're denser than 1.4. Whatever floats here, I can take, dry it, weigh, and then analyze for ash. So then whatever I get in the floats is what's shown in that table. Okay, so if I collected 100 kilograms overall, then what's shown is percent of floats in the first one, percent of floats in the second one from the 100, and percent of float in the third one from the 100. Okay, I'm just taking 100 kilogram as an example. You could collect 115. So we just say percentage of this one from 115, because the total float that we collected is 115. Okay, so it's just an example. So why do we get this? Why do we get this one and these ones? So the floats here are because they're lighter than 1.3. The sink here is because particles are denser than 1.3. Okay, and then when I take this one and put it through here, I'm expecting some particles have density between 1.3 and 1.35. That's why they float here. Okay, so again, when I put that one into 1.35, some particles float. That's taken, dried, and analyzed, and it can be expressed as a percentage of the overall floats. Okay, so this is what's going on. So that's why I say, if it's not making sense at this stage or why we're getting this one, I think it's probably a good time to ask. Okay. Otherwise, if everyone is okay with how we got this, then we can continue. Okay, no question? It's all good? Okay, so if I have this one, then what do I need to do? As I said, I need to construct cumulative floats curve, cumulative sinks curve, instantaneous ash curve, relative density curve, and distribution curve, from which I can determine different scenarios. Okay, so what is this one here? So that is actually So these three columns are what I've showed you in the previous slide. Okay, so this is percent of loss from the total for each of the specific gravity of media used, and this is the ask content in each of them. Okay, so 17.2 is percent of ash in this float, and 40.1 is percent of ash in this float, and so on. Okay, so then I can determine the quantity of ash. So if I know the mass or percent mass, and I know percent of ash in that mass, then if I wanted to know the quantity of the ash, I can then multiply the two together. Okay, so this column here is for quantity of ash. It is simply obtained by multiplying this column with this column. Okay, so there's nothing going on here. For column 5, again, it's taken from column 1. So what is this one shows? It shows simply the media density we used for each stage. Okay, so here I use media density of 1.3 to obtain this. Here I got media density of 1.35 to obtain this, and so on. So obviously if you take F, so F, the values of F here for each of them will give me this one here. So all I'm saying here is these are the separating densities or the media densities that we used for the sink and float experiment. Okay. Okay, so then if we know this, if we have this information, then the next steps will be taking cumulatives of my floats. How do I take the cumulatives of my floats? So if, for example, I say this is mass of plots, I want to get cumulative of them. All I have to do is for the first one is 9.5 taken from here. The second one here is cumulative for 1.3 and 1.35, which is the sum of this and this. Just like we did for cumulative passing size, if you remember, for particle size distribution. Okay, and what's the next one? The next one is at 1.4. So this is again 32.6 is obtained by adding 9.5, 9.7, 13.4 will give me the cumulative, which is 32.6. And we can go the same. So 50.4 is obtained by adding these four, 9.5, 9.7, 13, and 17.8. Okay, so again, this should be relatively easy. It's all about summing cumulative floats from top to bottom to obtain the sum or the cumulative of the floats for any specific gravity or any separating size, separating a specific gravity. Okay, so again, if that's okay for the floats, I will just do the same for the ash, in this case, quantity of ash. Okay, so this column here is obtained by summing column 4. First one, 47.8, 126 is obtained by adding 47 and 78. Okay, and 258 is again cumulative of 1, 2, and 3. 564 is obtained by adding all these numbers, 1, 2, 3, 4. 941, adding all these four. Okay, so again, I hope it makes sense because we're adding column 4 or cumulative of column 4. Then distribution is obtained by dividing 7 by 6. So column 7 by 6, column 7 by 6 will give you distribution of ash. So that one here is obtained by dividing 7 by 6. Okay, so that's done for the cumulative floats. So as I said earlier, if something doesn't float, it has to sink, right? So if I start with this 100 kilograms, if 20 kilogram floats, 80 kilogram has to sink. Okay, it's just typical mass balancing. So mass is maintained, it doesn't change. So if I do for floats, I can actually do exactly the same for the sink. So how do I do that? For the masses of cumulative sink here. Okay, so that's that column here. I hope you guys can see it. So now in 1.3 media, what floated was 9.5%. Must be because 90.5 of it is sinking. Okay, of 100, if 9.5 floats, 90.5 sinks. Next is 1.35, and in that 1.35, if you look at this number here, 19.2 is floating, cumulative. So the cumulative sink has to be 80.8. Simply 100 minus 19.2 will give me 80.8. Again, what I'm saying is if this much floats, then if I wanted to know the percent of the sink, I just have to take 100% minus the percent of the float, will give me the percent of the sink. Okay, so if you do that, then you should also get this number. It's simply 100 minus cumulative floats will give me cumulative sinks in percent. Okay, so I'm hoping everyone is following until now. Then the other thing is now the ash. So again, for the ash, now in the feed, I have a total amount of ash that I started with. Okay, so that total amount of ash, if you wanted to know, is actually 2746.6. Why? Because I'm summing all the quantity of ash I had from top to bottom, and this is what I should have in total. Okay, so that's the cumulative, that's in total. So if this is the total and I know the ash in the float, then I can actually work out the ash in the sink. How do I do that? So I say this is the total 2746, but when I go back to the first step here, the quantity of ash in that first step is actually 47.5 in the floats. Okay, so what is it saying? Of the total ash, 47.5 is actually in that first media at 1.3, went to the floats, which means 2746, which is this one, minus 47.5 should give me what has gone to the sink. So I know the total, I know the ash in the float, then I should be able to calculate the ash in the sink for each of those densities that I'm using for the media. Okay, so 2699.2 is obtained by subtracting 47.5 from 2746.6. Okay, so if I do that, then I can follow up with the next ones. So again, for specific gravity of 1.35, I know 126.1 is in the floats. Again, I say 2746 minus 126, I should get that one there. For the next one, 2746 is the total minus 258, I should get that one there. Okay, then I continue to complete this table. And again, have a quick look, maybe try a couple of them and see if they make sense. And then for the distribution of ash, again, I just divide 10 by 9, column 10 by 9, and I get this one here. Okay. So I think I am talking about this here, but I think the next slides may actually have the description of the process. Maybe I should have done it that way. Okay, so I think if you look here, you could actually see what's going on, maybe instead of me just talking on the table. So that's how you obtain cumulative floats. Okay, cumulative floats are obtained by taking the cumulatives of column 2. So that's what we have done. And for the sinks, that's how we have done. So again, I'm going to upload this so you guys can read it in your own time if you're not really getting what I'm talking about. Okay, but regardless, so these are exactly done, just like I was telling you. Okay, so the next step is to do instantaneous hash. Now, for instantaneous hash, what we're trying to do is, maybe I'll go back. So when I say, for example, in specific gravity range of 1.5 and 1.55, when we say the hash is 26.0, what we're actually saying is particles have specific gravity range from 1.5 to 1.55 in the float, but the average hash content is 26%, which means it's possible that some particles may have higher hash content, some particles may have lower hash content than 26, but the average is 26. So in this case, if you take, say, 5 grams from the sample and you do hash analysis, in the 5 gram, you have maybe a million particles. It doesn't mean that all those particles have the same hash content. We're just saying the average is 26. Okay, so 26%. So in a way, this actually tells you the average hash. But if you take any particle from there and quantify the hash, as I said, it could be more than 26 or less than 26, but the average is 26. We could do the same for the specific gravity. So in this case, if I say 1.5 and 1.55, some particles have specific gravity 1.51, some have 1.52, some have 1.53, but I can also get the average specific gravity. So that will be 1.5 divided by 1.55, sorry, 1.5 plus 1.55 divided by 2. So that will be 1.525, something like that. So that's the average specific gravity of the particles. But this one is saying a range of particles with specific gravity between 1.50 and 1.55. So how to work out the hash? It is actually based on the fact that the hash is average for particles with specific gravity between this. So in this case, I think we're taking the 1 point. So we're focusing on this one here for an example, 1.55 and 1.6, saying hash is 32.2, and that's the average. And for 1.55 and 1.60, we can work out the average specific gravity to be 1.575. And this is the average of the density of particles in this range. Okay, so for this average density, we can then work out the expected floats. Okay, so if you go back here, so I can work out average specific gravity. So this is the average hash. We can also work out average recovery of floats. So for 1.55 and 1.6, so it is the sum of 73.6 and 77 divided by 2 will give me the average floats. So then I can say for average hash content of 32.2, the average float would be 75.3, which is the sum of 77 and 73.6 divided by 2, which is the average of the two, and that will give me 75.3. So this is actually what we use as a value for the average floats, cumulative floats, for an average hash content in this specific gravity range. So if I go back then to the table itself, then that's how we complete this. Okay, so for specific gravity range between 1.55 and 1.6, average of these two is taken as 75.3. So that's how we got this number here. Now let's do any other number. Okay, so any other specific gravity range. So let's just say somewhere here at 1.4. So at 1.4 specific gravity, how do we get this number? 25.9. I will show you how we get that number. We get that number by simply coming here, and this is specific gravity range between 1.3 and 1.4. And I come back here, and at this particular range, which is 1.4, I take the average of 1.35 and 1.4, which is 19.2 and 32.6. So if you say 19.2 plus 32.6 divided by 2, you should get 25.9. Okay, so check if that makes sense, but should be obtained like that. So how do we get 70.6, for example? 70.6 is obtained because it is between 1.5 and 1.55. I come here, 1.5 and 1.55 cumulative floats. So I take the average between these two numbers, 67 and 73. That's how I get 70. Okay, so apply the same thing and you should be able to get all these numbers. Okay, if you just follow the same process. And the ash column 13 is simply copied from column 3. So it's just the ash percent. So it's copied there. So then if you did that, you should get this one's here, the instantaneous ash, and that's how we calculate that, and that's how you should complete the table. So the next one is, I think the last one is the plus or minus 0.1 distribution. For that one, what you need is two densities which are 0.2 apart from each other. Okay, so there's a description here if you want, but for any given separating density, you can find that separating density plus or minus 0.1. Okay, for example, let's take this one here, 1.5. So 1.5 plus or minus 0.1 means 1.4 and 1.6. Okay, so I hope you're following. So 1.5 plus or minus 0.1 gives me 1.4 and 1.6. So then I go to 1.4 and 1.6 and take the difference between the cumulative floats of these numbers. So 1.6 cumulative float is 77, 1.4 cumulative float is 32.6. So the difference between this is 77 minus 32.6, and that should be 44.4. Okay, let's do another one here. For example, at 1.7, 1.7 plus or minus 0.1 is 1.6 and 1.8, 1.6, 1.8. Now the cumulative floats corresponding to those is 83.1 and 77. So if I take the difference between these two, which is 83.1 minus 77, I should get 6.1. Okay, and do the same. So complete this one based on those calculations, and you should be able to get the plus or minus 1 distribution curve. Okay, so then to plot the curves, we just follow, for example, to plot cumulative floats versus ash curve, we take 6 and 8, column 6 and 8, we plot them. For cumulative sinks ash curve, we take column 9 and 11. For instantaneous ash, 12 and 13. For specific gravity, we take 5 and 6. And for distribution, we take 5 and 14. And we can then plot those curves. Okay, so if you took cumulative floats curve, it should look something like this. Okay, so that's column 6 and 8. So the cumulative floats is on the y-axis and the ash on the x-axis. And then we say, okay, now I'm going to run my sink and float, and I'm selling this to someone, and that person requires only 10% ash in the product. If I produce more than 10% coal material, then I'm going to get penalties for it. So maybe they will reduce the price, something happened, maybe they say they won't accept it. Okay, so maybe the requirement is to produce product that contains only 10% ash. So what we can do there is we can go back and say, okay, so from our sink and float experiment or the test we have done, if we're targeting only 10% ash, how much coal are we losing into the tails? Because it could be a lot of losses into the tails, but we want to know if it actually makes sense economically. Okay, so what you can do there is you go to the 10%. So that's here. So that is 10% ash in my product or in my floats. What is the recovery that I expect? So the recovery that you expect is somewhere around 40%. So this customer is requiring you to produce a 10% ash product. And for you to be able to apply sink and float and produce that material, you are going to get only 40% recovery, which means at the end of the day, after conducting your dense media separation, you're going to lose 60% of the coal into the tailings. So then you say, okay, this is just too much coal to lose, and I can't afford to be able to produce this high quality material. So maybe you might say to that customer, you can say you can't provide him simply because whatever you're losing versus whatever product you're making doesn't make economic sense, right? So that's one of the things you can say. Or if you can afford, if your processing is really okay, if you can live with losing 60% of the coal into the tailings, and if still that makes economic sense, then maybe you can afford it, okay? Or maybe you can talk to other customers which allow more ash. So maybe you say, how about I target something or someone who can buy 15% ash in my coal, okay? As I said, the ash is the impurity, tells you about the impurity. So you come here, so 15% is maybe somewhere around here. Okay, then from this curve, you say, so it's telling you maybe somewhere around 70%. So that's the 70% is the yield or the recovery. So you say you are only losing 30% of the coal, you're recovering 70% of it. So maybe you say, okay, this actually makes sense. I can make money. So rather than me trying to target 10% ash in the coal, it's better to target 15% ash in the coal and maybe sell it for a cheaper price. Okay, because you're trying to compromise the loss in coal with the lower in quality of the product. But it's either way, it's a trade-off. So you should say, this is working, this doesn't work, this makes economic sense, this doesn't make economic sense. But regardless, at least the cumulative loss curve or this washability curve is making you decide what to do with your scenario. Okay, so this is very important consideration, and that's why you need to make various decisions in terms of what you have in the ore, in terms of the potential of separation from a sink and float test, and in terms of the product quality you can make, and then you can negotiate the prices and things like that accordingly. Okay, so then I know now my recovery or my losses in coal. So then what do I reject into the sink or into the tails? Okay, so the sinks are the waste products, and I want to know how much ash is being rejected into that. Again, you can do the same. So if I want to target maybe 60% ash to be rejected into the sink, then you can work out what is the yield of the sinks. So you can actually see here that about 60% of the ash is in maybe about 25% of the sink, okay? Or in other words, if you're targeting 60%, 40% of the ash is in the float, and that float yield is over 70%. Okay, because this curve here is telling me in less than 30% of my sink, I can actually reject about 60% of the ash. Again, this is telling me that it is a reasonable rejection of the ash. In a small portion of the sink, I am rejecting more of the unwanted material or the ash. Okay, so that's one information that you can get from the cumulative sinks curve. And the relative density curve, again, tells you at a given, so this is the y-axis. I don't know if you see it clearly, but it's supposed to be cumulative floats. Okay, so it's a bit disordered, but that's fine. So it's cumulative floats. And this one is specific gravity. So again, if I target 70% recovery for my call, what is the media density that I want to be working at? So 70% recovery is here. I go here. 1.5 is my specific gravity of media that I want. Okay, I don't want to lose 30% of the call. Let's say I want to lose only 20% of the call. Then you're targeting 80% in that case. So 80% recovery can be obtained if you use media of 1.7 specific gravity. So when you increase the media specific gravity, you are allowing more and more material to float. Okay. As you allow more and more material to float, with that, you are allowing more and more coal to float. Okay. So regardless, at 80% coal, you can achieve 80% core recovery if you use a media of 1.7. So again, I'm also playing with what sort of media do I need to select when doing my sink and float. Okay, so do I use 1.2 or do I use 1.6 or do I use 1.8? Depends on what is my target recovery. And in this case, I can easily work those out. Okay, but for a given media density, I can work out what is my expected recovery and what my expected loss. Okay, so this can be used for that particular case. And the other factor is, as I said, that near gravity material. So I said near gravity material can make separation very difficult or very easy. If I have large proportion of near gravity material, then I will lose most of that because it's difficult to separate near gravity material to either the sink or to the float. And to quantify that, we use the distribution curve. Okay, so again, if you are working at, say, somewhere around 1.7 specific gravity of media, okay, so as I said earlier, at 1.7, I can make 80% recovery. And at 80% recovery, it's telling me that actually less than 10% is near gravity material. Okay, so within plus or minus 0.1 of 1.7. So the proportion of material that is within 0.1 plus or minus of 1.7 specific gravity is less than 10, which tells me that separation is easy. How about if I work at 1.45, somewhere here? It is telling me that at 1.45, there's a very high proportion of near gravity material, which means separation is going to be difficult. Although I get probably higher quality coal, my recovery is going to be very poor. And therefore, maybe I shouldn't target that. So okay, you can make these decisions based on, again, the distribution curve. So overall, that's what your washability curves look like. So I showed you individually what they are, but you can put them in one scale and compare them as well. Okay, and directly read from the curve and see what you can run different scenarios, and based on those scenarios, you can see what sort of recovery and grade you can target. Okay, I'll show you another example. Again, before I go to that one, any questions? Is it starting to make sense? Or is it really still confusing? Just let me know what you think. It's all good? Yeah? Okay, so if that's the case, then I will probably show you another example of the same sink and float data and finding different information. So again, this is something you can do, okay? So you have various densities of media that you use, collect various floats and express them as a percentage. And in each of those floats, quantify amount of ash And the question is to complete the table based on what I was showing you earlier. And once you complete the table, you plot the curves. And from the curves, you can answer some of these questions. For example, if I target 10% dash, what's my yield? Okay, what my recovery? And what is the specific gravity of media that helps me get that yield? And is it going to be an easy process or a difficult separation process? So these are some of the things you can answer based on the washability curves that you draw. So because I can't really track who is doing what, okay, usually if it's a face-to-face class, maybe I can help you guys with your calculations and we can do it slowly, but because it's really difficult to get feedback at this stage, so what I will do is just show you what the data looks like and what information we're getting from those. Okay, so if you did your calculations correctly, then that's what you should get. So that's cumulative curve, so cumulative floats, ash, and distribution. And this is for the sink. So if 40% floats, 60% sinks, okay, that's just based on that. And we can complete all this table, just like I showed you earlier, from which, so again, this is just an example of how you can do it, from which you get these curves for washability. So that's cumulative floats curve, and that's cumulative sinks curve, that's relative density curve, and plus or minus 0.1 specific gravity curve. And based on this, then you can answer these questions. Okay, so if it's 10% ash, what's the yield at 10% ash? For that, we use cumulative floats curve. So we come here, that's the blue line or the blue curve. So we come here and we say somewhere here is where I should target 10% ash. And from that, the corresponding yield will be this number here. Okay. So it's close to maybe 70% or somewhere around there. Okay. And the next question is 10% ash gives you about 70%, let's say roughly, and determine the specific gravity required for that. And all you have to do is then go to the relative density curve, and at 70% for probably 75% or whatever for that particular value, I can then read the relative density curve and find the cumulative specific gravity. So somewhere here, and maybe it's somewhere here on the red line, and I go back here, and maybe somewhere around here might be where I get the relative density on the x-axis. So maybe it could be somewhere around 1.8, 1.85, somewhere around there. So that is the density of media required to obtain 10% ash. And then at 1.8 or 1.5 specific gravity of media, is it going to be a difficult separation or not? So again, I go here and I read from the plus or minus 1 specific gravity curve. Okay, so I go up here and I get very low number, definitely less than 10%. So it's telling me, this curve is telling me that separation should be relatively easy. So I should be able to attain that separation at a relative ease. Okay, so these are some of the things you can obtain. And the actual numbers, if you want to read them, I think the the yield is about 77 and specific gravity is about 1.85 and the percent near gravity material is about 5%. Okay, so obviously this is just a rough estimation, but you can read directly from the x-axis and the y-axis to get more accurate values. So all I'm trying to show is the methodology on how you can do it. Okay, so hopefully when I upload this one and you read it slowly on your own time, maybe you refer to some other texts, it becomes clear as well. But use the opportunity to ask questions. Okay, so you can still ask me questions if something is not quite clear or whether you want some clarification, just feel free to ask. Okay, there's some chat from Mulukan. I don't know if it's to do with the connection or if it's to do with the topic I'm discussing. So it is some challenging. I don't know. Do you have any question, Mulukan? Are you talking about what I'm discussing here? Okay. Everybody's quiet. Does that mean there's no question? It's good. Okay. All right. If no questions, that's it for today. I will see you next week. Okay. Thanks, guys.